Yeah. So thanks a lot to the organizers for the invitation. And yeah, so the main part of this topic that I will present, which is based mostly on work done in collaboration with Georg Graffeld and partly on the work that also Günther presented a moment ago. Is again on fast neutrino flavor evolution, which is a topic that we've heard a lot about by multiple people in this conference. But the approach will be more on trying to construct a framework which could allow us, in principle, to understand intuitively what exactly motivates these fast instabilities to happen in the first place. So that will be the main motivation, in a sense. And of course, I will review the basics, which you have heard reviewed multiple times by Irene, Luke, Günther, also last week. So we know that flavor conversions can happen for individual neutrinos without having to talk to each other. We know that that happens because neutrinos, despite being produced in flavor eigenstate, so for example in muon neutrino eigenstate or election neutrino eigenstate, for the purpose of this talk I will always fake that there are always two neutrino eigenstates, two flavors. So even though they are producing interaction eigenstates, that's not how they propagate. The propagation eigenstates are different, are superposition. And so in a typical quantum mechanical fashion, even though we produce them as a muon neutrino, they will develop into a superposition of election and muon neutrinos. This is individual neutrino flavor conversions. It's not what we're going to be talking about. So fast collective neutrino flavor conversions, which are the only kind of collective flavor conversions I will talk about, are in fact conversions that happen on time scales and length scales much more rapid than the typical ones associated with the mass. In fact, as is often said, they could nearly happen even for massless neutrinos. They really have very little to do with the mass of neutrinos. The general idea, what they really have to do with is weak interactions. That's what the fast flavor conversions have to do with. The general idea is that if we have a thermal, or not a thermal, but a bath of neutrinos, a medium of neutrinos, if we have even just one neutrino that happens to be in a superposition, so not exactly in the election eigenstate, but with a tiny superposition with a muon eigenstate, then by weak interaction, that neutrino creates a weak potential, and another neutrino, a test neutrino, can feel this potential and convert into something else. So it can turn into an amplitude. So in other way, quantum superposition, the idea of having some neutrinos that are quantum superposition is some kind of infection, because if we have one neutrino that is in such a state, can turn another one into such a state. And you can understand that this, of course, has the potential to lead to an explosive process in which we have a few neutrinos in a superposition, but they turn a lot of neutrinos into a superposition. This is just a prerogative. It doesn't mean that we have the conditions for that to happen. And it will be the main purpose of my talk to understand what are the conditions under which this can happen, actually. This can turn into an explosive instability, but you can see where this can come from. So it comes entirely from weak interaction potentials. And another feature of these collective flavor conversions, I've talked about a medium neutrino and a test neutrino, but you understand, of course, that this distinction is completely arbitrary. There is no such thing as a test neutrino. When we are in a real environment, there are only neutrinos, and they are all medium neutrinos, and they feel the effect of each other. So this process is, by definition, nonlinear.
Are they the same as for neutrinos, as you have written, or they are different?
You mean these alpha E and alpha B?
Alpha E, alpha mu.
Well, this was just meant to be to imply that in a real environment, you can have some neutrinos that are in a superposition state.
For neutrinos and antineutrinos, as you wrote them, are the same. Is that the case, really?
Ah, you mean like, yeah. I mean, the physics is very similar for neutrinos and antineutrinos in the sense that if you have antineutrinos, they also...
No, it's not this. I'm asking something very simple, very simple. Alpha E and alpha mu in the neutrino linear combination, in the antineutrino linear combinations, are the same quantities or
they have
different?
The same physical meaning.
No, they have the same physical meaning, but...
Ah, no, sorry, notation. Yeah, they are not the same number.
They are not the same. This
sorry,
is all.
notation.
Thank you.
Sorry, yeah. Yes. So, so they have the potential to develop into an instability. Then the question is, does it matter for the phenomenologists? I mean, the talk by Irene, I think, reviewed this much better than I could do here. So I will just say that, obviously, if you want this to develop into a stability, you need to have large densities because you need this effect to be large. It's not enough. There also need to be additional conditions, which are the main topic of this talk. But anticipating what has been done in the literature, it appears that these conditions usually are met in the majority of supernova and neutron star merger simulations that are available. So it appears that this process is interesting for realistic astrophysical environments. It also appears that it can affect observable properties of these quantities. Obviously, they can affect what neutrinos we will see at Earth, for example, from the next galactic supernova. And it also appears, much less trivially, that they can also affect the evolution of a supernova. Irene has talked about this yesterday, so I will not go into any more detail. The main purpose of this slide is just to motivate and say, this is interesting for the phenomenologist. But this is interesting also for the theorist. This is by definition a many-body system. The interactions are many-body interactions. In a sense, it's very similar, for example, to magnetic interactions, where we have spins interacting with each other. In this case, we have flavored neutrinos interacting with each other. So it is a many-body system, and in some sense, it's one of the most exotic many-body systems we can think of, because usually we think about many-body systems on Earth, which are driven by electromagnetic interactions, perhaps sometimes strong interactions in nuclei. This is, as far as I know, a unique case in which it is a weak interaction that is driving the many-body behavior. But that's not what makes it interesting, actually. What makes it interesting for the theorist is that, as I will try to discuss in more detail later, this process naturally develops in homogeneities, even if you do not have inhomogeneities to start with. Even if you have a supernova that is generally homogeneous on scales of hundreds of meters, for example, this process rapidly develops things becoming inhomogeneous on scales of centimeters. So it is an intrinsically multi-scale problem, which makes it challenging for numerical implementation, interesting for theoretical understanding. We have many examples in physics of multi-scale problems. Unfortunately, not all of them are very promising because they require decades even just for very basic understanding. So we have turbulence, we have convection, we have magnetized turbulence. We have many, many more examples. Of course, this is just a very brief list of some of the most well-known. So fast flavor conversions in this sense is just a very last addition to this list. And how have we proceeded as theorists in trying to understand and tackling this problem? Usually, we do what other people, also Luke has discussed, as subgrid recipe. So we try to understand what happens at the small scales in some intuitive sense, and then we put it back into the large scale simulations to understand what they do. But one thing that we can learn from history and from the history of these topics is that usually these subgrid recipes have required a careful and deep understanding of the intuitive features of these processes. You can think about turbulence. Of course, the subgrid recipe that people typically use is the Kolmogorov theory, which is based on a very deep intuitive understanding of cascading of power from large scales to small scales. We have convection, which is based on, usually it's treated by mixing length approximations, so an intuitive idea that things can be transported over a certain length determined by usually phenomenological parameters. Magnetized turbulence also is treated usually by an idea of cascading of power. So the status in which we are now is, what is the subgrid recipe, but also what is the intuitive picture that could help us building that subgrid recipe? And that will be the main purpose of my talk, trying to build some intuition. This is a topic that is often presented as either built on very complicated mathematical equations or taking those equations and putting them on a computer. Both of them are, of course, very constructive strategies, but at the same time, can we interpret those results? Can we understand them intuitively? So as a brief outline of what I will be talking about, I will start with quantum kinetic equations. These are the tools that help us understanding the topic. Gunther has discussed them at length just now, so I will be very quick on this point. But then I will try to discuss when can we say in advance that the system will be stable, will not exhibit instability. It turns out that there is a very simple argument based on conservation laws by which we can immediately claim that a system will be stable and not exhibit any instability. And these stable systems have received a very limited amount of attention in the past years, for the very simple fact that stable systems do not exhibit instability, so they are seen as practically useless because they don't do much. On the other end, if we want to understand intuitively, of course, stable systems are the simplest. So it's a very good starting point, I would say. And so I will try to understand what exactly happens in a stable system. And I will show that understanding what happens in a stable system allows us to understand what actually drives instability. Why can we say that a system becomes unstable, and what is the mechanism by which it becomes unstable? So I will start with quantum kinetic equations again. As I said, these instabilities mean that quantum neutrinos that are quantum superposition turned other neutrinos into quantum superposition. What is the mathematical tool by which we describe this? As Gunther has already introduced, it's a density matrix. The element of a density matrix tells us the probability that the neutrino is in the election state or in the muon state, but what we are really interested in is the off-diagonal term, which is the product of the two amplitude. That means if a neutrino is in a superposition eigenstate, this object will be different from zero. So when I say instability, which in the qualitative sense means neutrinos becoming superposition, in the quantitative sense, it means that this object becomes large. It starts from being very small and it becomes large. And if we want to understand how it becomes large, we need to understand how this object, the density matrix, evolves in time. So we need to understand the quantum kinetic equations. Gunther has introduced them just now, so I will be brief and just focus on the physics, on the physical nature of these processes. The main ones that are of interest for these fast instabilities are two: advection, which is the term that is present in any Boltzmann equation, essentially just describes the fact that neutrinos move. So if you have a neutrino in a certain state here, it will move at another point here and transport with itself its flavor state. So this is what is described usually by advection. The other term is interaction. So it's the neutrinos interacting with the weak interaction potential produced by all the other neutrinos at the same point in space. This is, of course, what we were understanding as a term that triggers the instability, this weak interaction potential. It's also the term that resembles the most a magnet, because in a magnet we have the same kind of thing. We have exchange interactions by which a spin can feel the potential generated by another spin. But what is interesting is that this term alone is not the one that determines the instability. Both of these terms determine the instability, the interplay between interaction and advection. And this is not the first case in physics in which we face something similar, in which instabilities are determined not just by interaction, but also by movement. The first historical case, of course, was in the case of plasmas. In plasmas, where we can have instabilities, we can have, by definition, electric fields that grow and are transported away by electrons that move. So the typical timescale associated with this interaction term is of the order of the nanosecond. That means that a neutrino turning into a quantum of eigens in the quantum superposition in a nanosecond will move by a centimeter and transport that information to another neutrino that can move in another random direction and transport that information in another place. That's where what we usually call spontaneous breaking of homogeneity comes from. Even if we start with something that is generally homogeneous, the somewhat randomized motion of neutrinos that can stream and transport the instability in other place is what breaks the homogeneity and leads in general to the development of small-scale features. Okay, so these are the general feature of the equations that we need to understand what comes afterwards. So from now, I would like to go into the question that I anticipated. Can we understand when a system is stable? This has been already anticipated by various people who have talked about conditions for instability. But until a few years ago, this was mostly understood in a very mathematical sense, in the sense of taking dispersion relations, which are matrices, and understanding it. Yes?
Explain what do you mean by stable and instability?
Yes. So as I mentioned, the presence of this weak interaction allow, in principle, for the off-diagonal term in the density matrix to grow. Because it means, in principle, that even if initially most of your neutrinos are neatly in flavor eigenstate, they can deviate sizably from those flavor eigenstates. But this is in principle. If this happens, the system is unstable. If this does not happen, it's stable.
Which means flavor conversion.
Yes.
So instability means flavor conversion.
Instability means large flavor conversions triggered by self-interaction.
That is, flavor conversion with relatively large probability.
Yes,
okay.
Which grows exponentially in time. Yes,
okay.
That's the point.
I'm sorry, the fact that the system is unstable doesn't mean that you have a large conversion capacity. It can be unstable.
What I mean is that the off-diagonal component grows exponentially. Then to what value it grows is another question, but it grows exponentially. Yes. Yeah, so as I was saying, so to go back to the question, the fact that there are self-interactions doesn't mean that things will grow exponentially. Can we predict under what conditions things will grow exponentially? And at the very least, we can predict when they cannot grow exponentially, and we can do it based on conservation laws. So the weak interactions that trigger the instability, by definition, conserve lepton number. They conserve election lepton number. They conserve, as you can easily see, the difference between the election lepton number and the muon lepton number, which usually is called E minus X lepton number. You can easily see that in each of the processes that trigger the instability, this quantity is conserved. By itself, this statement, which is non-trivial, allow us already to predict when a system will not exhibit an instability. So if we have neutrinos going in various directions, So cosine theta is, for example, the angle made with a certain fixed direction. Then we can look into the angular distribution of these neutrinos along each of these directions. And we can look at the distribution of the E minus X lepton number along each of these directions. If this quantity is always positive, then what we can already predict is that an instability cannot ensue. Because if an instability did happen, that would mean that some of these neutrinos, so just to see, if this quantity is always positive, it means that we have an excess of electron neutrinos in every possible direction. If there were large flavor conversions, one of these electron neutrinos would have to turn into a superposition with a mu neutrino. And so its contribution to the E minus X lepton number would drop. But nothing can drop here because the integral of this number must be conserved by the conservation law that I just introduced. So there cannot be any instability if this quantity is always positive. This is usually phrased in a community by saying that we need, yes? Yes. Yes, yes, yes. This is only neutrino-neutrino refraction, as it's called. Neutrino and antineutrino are interacting as well. That's why when I say E minus X lepton number, I generally, it doesn't have to be. It could be asymmetric, and some of these instabilities develop because of the asymmetry. What I'm neglecting in this treatment is matter effect. So symmetric in neutrinos and antineutrinos. It can make a difference. But simply because if you start with a completely symmetric system, this is zero. So this curve is zero everywhere, and you cannot have any instability at all. Yeah. So this is included. What is not included is matter refraction, which does not seem to make any difference for the onset of instability. But yeah, I just wanted to keep it. Yeah. Fast modes, yeah. So it's only for fast instabilities. I introduced it in. I mean, many of these results are true more generally in a broader sense, but I will not go into these subtleties. I mean, yes, it is important. If you have an identical number of electron neutrinos and electron antineutrinos, you don't have any instability. Not have sorry, let me say, not have any instability in this fast sense. Yeah. Yeah. No, I'm not saying that they don't deserve attention. What I mean is that, yes. It's not considered in this case. So the matter term is not considered in this case. Matter is because of vacuum. Okay, yeah. Okay, in the sense that okay. But even if those individual conversions would happen on much longer timescales, right? So it's yeah. Yeah, so as we said, if there is no crossing, meaning that this curve never crosses the zero and it's always positive, there can be no instability. Now we ask ourselves what happens if this curve can cross the zero, so it has an ELN crossing, as it's usually called. Does it exhibit an instability? Well, it's not so trivial. For now, we have only proven that if it doesn't exhibit an instability. So now we'll slowly go into the case in which a crossing happened. But first, we start with the case of a stable system. So we start with a case in which the system does not have a crossing, and we want to understand the meaning of stability. When I say the meaning of stability, I mean that if we take the system, we can try to force off-diagonal elements, and then we want to understand what happens to those off-diagonal elements. So for example, we can initialize our system with an off-diagonal element of the density matrix that is periodic in space. This is a completely arbitrary choice. You may think, well, it could be anything else, but as we know from Fourier, we can always write any possible spatial dependence of this rho E mu as a periodic in space pattern, right? So this is what we usually call a flavor wave, meaning that it's a periodic modulation of the off-diagonal the off-diagonal element of the density matrix. And then we ask ourselves, what does this flavor wave do? Does it remain in the system? Does it explode? I mean, it cannot explode, we know it because the system is stable, but what does it exactly do? So obviously, this wave is going to move with a certain phase velocity. You can go with the equations and find the phase velocity. This is not, I don't want to go into equations, but this wave is going to move, and it's going to move with a certain phase velocity along a certain direction. And so we may ask, do the neutrino feel any effect from this collective wave, collective flavor wave? Because of course, if there is enough diagonal element in the matrix, in the density matrix, it generates a weak potential, and this weak potential can affect the neutrinos. Can the neutrinos feel an effect from this flavor wave? Yes, for example, with a certain x coordinate, and then it will move in time with the phase velocity that comes from the equations. Yeah. So neutrinos obviously move with the speed of light, but they move in any direction. So let's imagine to have a neutrino which is moving to a certain angle compared to the horizontal direction, right? A certain angle theta. So the velocity along the direction of the wave is the velocity of light times cosine of theta. And now we let the system run, and we look at what happens, what the neutrino feels. Now, if the neutrino is moving with a velocity that is different from the phase velocity of the wave, the two rapidly dephase in the sense that the neutrinos is always seeing a different point of the wave. For example, here it's in a dip, but here it's in a peak, and then it's in a dip again. So the sign of the force that the neutrino feels from the off-diagonal flavor wave changes all the time. And as a net effect, the neutrino does not feel anything. It's not sizably affected by the interaction with the wave. But we have a special case which happens if the neutrino is moving with the velocity along the direction of the wave exactly equal to the phase velocity of the wave. In this case, the neutrino is fixed relative to the wave, so it always feels the same effect, and this same effect can accumulate. And so there is a sizable interaction between the neutrino and the flavor wave. And what does this sizable interaction do? It cannot make the wave grow because the system is stable, so it can only do one other thing, it can dump it. So even though we try to force a flavor wave with off-diagonal coherence along the system, the flavor wave is damped. And this particular mechanism of damping is well known since the 50s. It's usually called damping. I say this particular mechanism of damping because it's not driven by collisions. It's not a thermodynamical damping. It's a damping that, not thermodynamical, I mean collisional damping. It's a damping that comes entirely from a resonant interaction between the waves and those portions of the neutrinos that move exactly in phase with the wave, which we usually call resonant neutrinos for obvious reasons. So that means that for a stable system, waves are damped, and this is usually described by saying that the flavor wave can be resonantly absorbed by Cherenkov processes by the neutrinos. You can easily see that the condition that the phase velocity of the wave is equal to the velocity of the neutrino is exactly the condition for Cherenkov absorption of a wave. Yeah, so non-adiabatic that the net effect is zero. Yeah, I mean, such a level of non-adiabaticity that yes, the neutrinos. But the point is that in a realistic system, you have neutrinos streaming in all directions, so you always have some neutrinos that move in, yeah. Yes. Matter potential, you mean the potential generated by the neutrinos? Yes, it's completely neutral current, yeah. This flavor wave, yeah. So when neutrino feels, because it moves along the wave, it feels a rapidly changing in time flavor, neutral current potential generated by the flavor wave, yes. No, I mean, it's, so, yeah. So rho e mu, so the potential is not generated by a neutral medium. The medium is not neutral because this is a off-diagonal component. So it's the medium that generates the difference between what an electron neutrino and a mu neutrino feels. Yeah, of course it becomes very confusing because the medium is what it's feeling the effect anyway. I mean, but that's why it's nonlinear. But yes. No, I mean, you don't have a, if you have a compensation, it's because the E minus X lepton number is 0, and then you don't have any, any large effect. But in general, the flavor potential, the weak potential that is generated by this term in the density matrix is felt by each neutrino according to its flavor. Yes. I'm not sure I understood. You said Gaussian wave packet? What is much smaller? I just can't hear. Sorry. Okay. I mean, just to make sure, I'm not talking about Gaussian wave packet. This is a fully plane wave in the sense that it's infinitely extended because we are looking at idealized cases for now. But I'm not sure it is. Okay. So in the sense of what happens to a stable system, what we have found is that if we initialize the system, usually the kinetic energy of these neutrinos is a huge number. It's of the order of MeV per particle, whereas the interaction potential energy due to weak interaction is of the order of 10 to the minus 13, for example, GeV per particle. So it's a very, very small number. And then we initialize the system with a small amount of energy in potential due to neutrinos that are not in a flavor eigenstate. And as we let the system go, this off-diagonal energy disappears because it is damped. And by what Gunther was discussing in his previous talk, it essentially migrates to the kinetic energy and the on-diagonal energy of the system. But now what happens if we try to change and slowly distort the distribution until it develops a crossing? You might think of this case as somewhat idealized. It's actually not, because we usually think of distributions that are already unstable to begin with. But to be fair, case, because if we have a distribution that is already unstable to begin with in a supernova snapshot, for example, it means that a supernova snapshot is wrong because it cannot have reached that point, right? The instability would have been saturated before. So what happens if we start with a distribution that has no crossing and we slowly deform it until it develops a crossing in such a way? Well, what happens is that the flavor waves that are resonating with neutrinos on this part of the distribution are still going to be damped because nothing has changed for these neutrinos. They still are more or less the same. But if we have a flavor wave that is resonant exactly with neutrinos at the crossing, they have no lepton number to interact with. The neutrinos that are there are essentially equal amount of electron and mu neutrinos, or of electron and anti-electron neutrinos. There is no lepton number to interact with. A wave that is resonant exactly with neutrinos at the crossing is not damped, because there's nothing to interact with. And you can see where I'm going here, because if these waves are amplified and these waves are damped, and these waves have a 0 growth rate, then these waves, the waves that are resonant with neutrinos in the flipped region, must be amplified. And that's the basic idea of what we have shown mathematically in our paper, that the waves that are resonating with neutrinos in the region are actually the waves that are amplified. So this is what I meant when I said trying to get an intuitive picture of this fast instability. What causes the instability is the fact that what previously was Cherenkov absorption of flavor waves by neutrinos has turned into a Cherenkov emission of flavor waves, which is kind of compulsive and therefore leads to a growth of the flavor conversions. So by this intuitive prediction, understanding, we can already make a qualitative prediction about what we expect about the instability. Because if these neutrinos are the ones that are emitting compulsively flavor waves, these are the ones that are expected to be the most affected by the flavor conversions after it will become large. And indeed, this prediction is already verified by numerical simulations of these conversions into the nonlinear regime. I think for those that were here last week, Zewei showed, for example, the results of small-scale simulations of small boxes, and they do find that the neutrinos in this part of the crossing are the ones that feel the largest effect because they get into equipartition, whereas the neutrinos in this part of the angular distribution are usually the ones that feel very small effect. Of course, to make quantitative prediction, we need to go into understanding what happens when the perturbations becomes large. And when perturbations become large is where things become complicated, because we need to treat them linearly. They are not small, so they cannot be treated as a perturbation. So one thing that we have tried to do is a first step in this direction is to understand the mechanism of relaxation of this instability in a very in the simplest toy model one can think of that exhibits all the features of the instability. So when I say the simplest toy model, we take a very small scale system which contains only neutrinos going in exactly two directions, one direction that is forward, one direction that is backward, and we assume that there are election neutrinos in the forward direction, anti-election neutrinos in the backward direction. There are less anti-election neutrinos than election neutrinos in this case, in this example. Then this system is just a simple two-beam system in the sense that there are only two directions. And we can look it up numerically. Just focus on the gray curve. I won't have time to discuss the colored curve, but if you focus on the gray curve, these are the number of electron minus mu on neutrino, so the E minus X lepton number, for the forward moving beam and for the backward moving beam. And what you can see, so this is the strong beam in a sense because it contains the most neutrinos. This is the weak beam which contains less neutrinos. And you can see that the weak beam rapidly is rapidly driven towards equipartition. So in this sense, this numerical statement confirms what in more complicated cases has been found by groups focused on numerical simulation. The question is, can we give a theoretical interpretation of that? And what we have done is to pursue an approach that is just one step forward compared to the linear treatment of the perturbation. The general idea is the quasi-linear approach, which is well known in plasma physics and is the way these instabilities are typically treated in plasma physics. The physical idea behind this approximation scheme is to treat only the small scale fluctuations as linear. So we treat them with linear perturbation theory. Linear perturbation theory is, at least in principle, simple. So we can find analytically how these small scale fluctuations grow, but then their feedback on the large scale system is treated non-linearly. That's why this is called quasi-linear treatment. Now, what we find by this quasi-linear treatment is that we directly predict that the system sticks to the closest state that has no crossing. So it sticks to the closest state that is linearly stable. In this case, the closest state that is stable is a state in which these neutrinos, the weak neutrinos, are in equipartition because they go to zero and then there is no crossing. So in this sense, for this very simple toy model, we can make a prediction that is well verified by numerical simulation. Extending these, of course, to a larger system is much more complex task. But yeah, I mean, I'll just come to my conclusion. The main topic that I wanted to discuss is whether, or the main question I wanted to pose is whether it is possible to understand in an intuitive fashion these fast instabilities so that when we look at a large-scale numerical simulation, we can try at least to interpret those results rather than just describe them. And we have shown, and this was, actually Luke was working on something very similar in his language of mixed dynamics. But what we have shown is that conservation laws can protect a system from instability. In particular, the E minus X lepton number conservation can protect the system from developing an instability. And we have shown that the mechanism by which an instability develops is essentially a resonant mechanism. The neutrinos that are beyond the angular crossing can resonantly emit flavor waves until they lead to very sizable flavor conversions. And then finally, as a first step towards maybe what could become at some point, but we don't know, a subgrid recipe, we have tried to treat the instability quasi-linearly, which is again the usual, most of what I have discussed is something that is reintroduced in the context of flavor community because most of this was already known in the context of plasma instabilities. We have tried to treat the local relaxation of instability by a quasi-linear framework. For very simple toy models, this makes the correct prediction, but very simple toy models is not our final aim. So obviously this is just a very preliminary first step. But yeah, thanks very much for your attention.
Flavor wave.
Yeah, so as I said, I mean, flavor wave, generally speaking.
Terminology, I mean.
Yeah, no. But when I introduce it in a very improper fashion because what I said is a periodic modulation of the off-diagonal elements of the metric, of the density metric. So this means I call the flavor wave when rho E mu has a periodic modulation. This is not a very formal statement. The formal statement would be you write a kinetic equation and then you look for the normal modes of the system. So you try to look for solutions of the collective equations that behave as plane waves, for example. So they behave as Yes, but the key point is that this is periodic in space and time, and the reason it's periodic in space and time is because it's maintained by the collective interaction between these neutrinos. Yeah.
Can you show? No, later. Okay. Can you show the one slide before the last?
Yeah.
Again, it's no, the previous one.
Ah, sorry. This one?
Now, space-time fluctuating, but average leads to removal of angular crossing. What do you average over?
Small distances. So that means we have a box, for example, that contains many, many periods of oscillation, and you can average over the very many periods of oscillation, and the space averaged thing.
But, I mean, physically, to what that corresponds? Uncertainty in the point of neutrino production?
For example, I mean, what you should imagine is that in a real supernova, what we have is a volume that can be 100 meter long, and the typical length scale of these oscillations are centimeter long.
No, this I understand. So the uncertainty is related to the fact that you don't know where neutrinos are produced.
Yes. I mean, where they are produced. And
okay.
Not just that. I mean, let me clarify. It's not just that. It's also that, of course, in a real supernova, you also have a small amplitude turbulent fluctuations in the matter, in the neutrino density. So all of these things have small fluctuations that we cannot predict in a realistic way. So that's why we average over small scale. And then there's also the point of where the neutrinos are produced. So it's a combination of all, let's say.
I understand that these flavor waves, I mean, what you mean by that. They're just plane wave, like solutions of flavor evolution equation. But when you say emission of flavor waves, what do you have in mind?
Mm-hmm. So, of course, yeah. So this idea of emission of flavor waves, which was introduced in the context of plasma physics for the emission of plasma waves, was introduced mostly to match with the language of particle physicists, because then you can write things in terms of Feynman diagrams, which can help some intuition. What I mean with this is just, with rank of absorption, what I mean with this is that the flavor wave is damped in time as a whole. It's a classical wave. So you can imagine it, if you want, as a classical state made of many quanta. And these quanta are absorbed one by one, but when you look at the classical solution, you just see an exponential damping. And that's the way, I mean, that's the same thing actually for the Cherenkov of absorption of emission of electromagnetic wave, right? If you think about Cherenkov emission of electromagnetic wave in solving the Maxwell equation, what you see is just a solution of the electric field that grows in time.
See, like your test neutrino is interacting with a classical field.
Yes, correct. Yeah,
okay.
yeah.
I have two comments,
Yes.
just comments, complementary. To my knowledge, the first, there were others, connections to plasma physics was done, for example, in the work of Lisi and collaborators in the context of linearized, when they classified the different instabilities, you know.
So that's
so that was
paper,
already a few years ago.
Yeah, that paper introduced the plasma language, but in a completely different context, because what the paper was discussing was the difference between absolute and convective instability. Voilà. So it's a somewhat very different topic than what we're trying. Yeah, but yes,
but
the first mention of plasma nomenclature was in that paper. Yes.
Voilà. That was my first comment.
Yes.
And another comment is, here in the context of neutrino physics, we are very much interested in instabilities, flavor instabilities. And you said, okay, stable system, we are not so much interested into it. I just want to complement it and say that there are other fields, like in the context of atomic nuclei, you are very much interested in stable systems and also in the linearized variation of stable system, because the stable system have the properties of an atomic nucleus. So it's an entire branch of the field, while when you linearize around the stable solution, which is the ground state, you are creating excitations.
Oscillations, yeah.
Voila. Like,
yeah. I mean,
so I just want to make this bridge between neutrino many-body systems and other many-body systems. And the intriguing thing is that we are so much interested in instabilities here, while in the context, for example, of atomic nuclei, we are very much interested also to the stable systems. Yeah, so if I have time to add just a comment on that, because I did not want to comment. So yes, as you said, the interest in stable system is something that in our community has been mostly, lacking, but for obvious reasons, we are interested in the phenomenology. On the other hand, even if we are interested in the phenomenology, and this is a point that was first emphasized by Luke actually in his Mr. Dynamics paper, and then we also tried to go with, is that unstable systems as they are do not exist in nature. They cannot exist in nature. And actually in plasma physics, for example,
the interest in the beginning was on stable systems for the simple fact that nobody believed that unstable system could possibly exist. And then the interest moved later. So in our community, we have somewhat gone the opposite direction. But in some sense, one of the purpose of our paper here was exactly to show, I mean, I didn't have time to comment on these colored curves, but one of our purpose on this paper here was that the gray curves are obtained by starting with an unstable system, whereas the colored curves are obtained by trying to reach the same unstable system, but slowly. So we start from a stable configuration and we drive towards instability. And what we see is that for certain mechanisms by which we drive towards instability, we can find different conclusions. So in a sense, one of our main messages here was, again, connected with what Luke also has discussed in his adiabatic language with thermodynamics, is starting from when we think about starting with the most unstable configuration that we can, because we want to find the most dramatic effect that we can, but that's also the most wrong starting point to be. I mean, that's not meant to be a criticism, it's more like a comment, right? I mean, it's very instructive, but unstable snapshots of supernova simulations are not realized actually in nature, right? So that's...
Okay. If there are no more comments or questions, let us thank Damian again.